nanoHUB.org.
You can follow along with this presentation using printed slides from the NanoHUB. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
In the previous lecture segments, we had looked at more at the physics. What is the intuitive answer that you expect, or the unintuitive stuff you didn't quite expect, or the relevant device physics that was important. Now for you mathematically inclined people, we're going to do the math. Okay, so what does it take under the hood to compute all of that? So this lecture is called Direct Spatial Discretization in the 1D Effective Mass Hamiltonian and Open Boundary Conditions. Right? So now that's where the rubber hits the road. Oh. Always be prepared. So what we'll talk about is the effective mass tight binding Hamiltonian in 1D in the discretized Schrödinger equation and the quantum transmitting boundary condition as an open boundary condition treatment. So what you do is you have a device and you put it into a discretized mesh. And what we'll have is a left contact, a device, and a right contact. And in the central device, we solve the non-equilibrium transport equations. And in the left and the right contact, we assume that the contact is in equilibrium, and it's treated through self-energy. And for the first part, we actually assume that it's flat in potential. So let's do the very simple scattering-based Schrödinger approach. No non-equilibrium green functions, nothing fancy, something that you can find in textbooks. So you have the 1D effective mass Schrödinger equation, but written in a form where the effective mass can also vary spatially, which is in reality that happens. Aluminum gallium arsenide has a different effective mass than gallium arsenide. So you have this Schrödinger equation and you apply a finite difference approximation, so you spatially discretize it, and if you assume that the effective mass is constant, it gets a little bit easier. You can take a 3-point approximation for the second derivative, and you write the second derivative as just a point to the left, 2 on the center, 1 point on the right, divided by delta square. Standard finite difference discretization. If you write this in a matrix type form, you can say, well, a wave function on the left is coupled to a coupling matrix S, diagonal on the side J, and then J plus 1 to the right is coupled to another matrix element. But if M star, the effective mass is allowed to vary, which is true in real heterostructures, you got to work a little bit more on these S and these D's elements, a little bit more carefully. That is also true that you have to think about how you mesh this device a little bit more carefully. So in continuum approaches, finite difference, finite elements, what you typically do is you put the mesh point on the interface. Because you think of material A to B, the interface being a well-defined line. Right? That's what in continuum you do if you have any real meshing algorithms. Well, that's fine, but if you really think hard about it, you have, for example, a material like gallium arsenide, and let's look at the 100 crystal direction, where you have certain planes of atoms. You might have gallium arsenide, aluminum arsenide. Right? They just alter like that. But that means the true interface between the materials is actually between the atoms. Right? It's not on the atoms, it's between the atoms. So if you were to discretize this space in a typical continuum approach, you would put a mesh point here. There's no atoms there. It's kind of unintuitive. Why would you do that? Why would you put artificial, numerical, mathematical concepts in spaces that are void? You put the mesh points where the atoms are. That's a fundamental different thinking of atomistic versus continuum. Okay? In continuum, you discretize where the changes are. In atomistic, you discretize where the atoms are. And the formulations, therefore, are slightly different. All right. So if you do this in a simple fashion where you have your effective mass vary from mesh points to mesh points, and you assume that the wave function must vary linearly between mesh points, and that m star is constant across, you come up with a discretization that looks like this. If you assume that the heterostructure is on a mesh point, and you change it so where it's between mesh points, then you come up with a discretization like this. And if you are allowing the effective mass to change, then you come up with yet a third scheme. And it's the third scheme you ought to be using. This one uses the atoms as the mesh points, and each material has its own effective mass, and you satisfy the continuum wave functions and a continuum derivative of the mass change and the wave function change. So if you do that, and you have a 1D discretization scheme, you have a tri-diagonal matrix. You have diagonal matrix elements and off-diagonal matrix elements S. And you have a vector psi, those are the wave functions. And here you have, if you do an eigenvector calculation, eigenvalue calculation, that's what you would calculate. Okay, so that would be a typical system of a closed system matrix. Right, there's nothing open on the left, nothing open to the right, it's just a discretized space. So now what you want to do is connect this closed system to something that's open. Okay? So it's semi-infinite and it varies, no variations on the left, and semi-infinite to the right. So we'll add these two nodes, j equal to 0 and j equal to n plus 1 to the system, and we assume by scattering matrix approaches that we know what these wave functions are, what comes in and what is reflected and what goes through and is reflected. Okay? So you have a wave function coming in from the left, it has an amplitude and it has a propagation constant. Typically in the classical way you would say e to the ikx, but this is now a discrete form on a mesh, so it's z to the j minus 1. And you have a reflected wave with an amplitude that goes in the other direction, with the 1 over the z that you had here. On the right, you do something similar. You shoot in a wave from the right. It has a propagation constant that has a sort of delay to it. It propagates in the other direction, and the delay is the phase delay of sites n. And you have a reflected wave that comes back, and the propagation constant is again with a positive j, just like on the left, the a1, same sign, but it's phase shifted by n sites. Right? It's like the ijka, right? The a, the lattice distance that you have phase delayed this wave. And then what you do is wave function matching at this edge and at this edge.